Hey guys, today we are going to do SFD and BMD, that is shear force diagrams and bending moment diagrams. And today we are going to discuss all the standard cases for SFD and BMD. That is, we will do questions which will contain cantilever beams. That is, cantilever beams are beams in which one side is completely fixed. And simply supported beams are beams which are supported at both the ends. That is like this. And in overhanging beams, one end is supported while the other is anywhere in between the beam. That is, it can be over here. So this part is known as the overhanging part. That is why it is known as the overhanging beam. Now similarly, we are going to do questions which will involve UDL. That is uniformly distributed load. Now guys, this is very important as you will find this in every question. Now we will understand what is UDL. That is, suppose that a load is distributed evenly on a beam. That is, the force on every part of this beam in which the load is will be equal. That is, at all points of this beam in which the load is distributed, you will find equal amount of forces being applied. And similarly, UVL is completely different from UDL. UVL is uniformly varying load, in which the forces acting on the part of the load which are on the beam will be different at each point. That is, you will experience a different force over here and a different amount of force will be experienced here. That is, on this whole part you will experience different amount of forces. But in UDL, on each part of this load you will experience the same amount of force. Now guys, first we will look at the shortcut procedure to determine SFD and BMD diagrams. Then we will look at the sign conventions for SFD and BMD. Guys, these sign conventions are very important as they will be used in every question. So guys, please watch the complete video because I will be discussing very important concepts while doing the questions. Now guys, we will discuss the shortcut procedure to know the nature of shear force and bending moment diagrams. Now suppose that we have a beam in which no load is applied. So our SFD will also be a constant, that is, it will be a straight line. And our BMD diagram will be a linear graph, that is, it will go like this. Now suppose if we have UDL, that is uniformly distributed load on a beam, as we discussed before, that each point on this load will experience the same force. So our SFD diagram will come out to be linear. And similarly our BMD diagram will come out to be parabolic. And suppose if we have UVL, that is uniformly varying load, that is, as we discussed earlier, that each point on this load will experience a different force. So our SFD diagram will come out to be parabolic and our BMD diagram will come out to be cubic. Now guys, I am discussing these because suppose if you get UDL in your question and your graph of SFD is coming out to be constant, then you will get to know that you are doing the question wrong. And similarly, if UVL is given and your BMD diagram is coming out to be parabolic, that means you are not doing the question correctly and you have gone wrong somewhere. Similarly, if you do not get these graphs for the corresponding loads, then you will get to know that you are doing the question wrong. So guys, I advise you to please remember these, that if no load is given, what type of diagrams you will get, and similarly please remember what type of diagrams you will get when you have UDL and UVL, in order to find that whether you are doing the question right or wrong. Now guys, nextly we will be discussing the sign conventions that we will use for solving questions of SFD and BMD. Now guys, we will discuss the sign convention that we will be using for SFD and BMD while solving our questions. Now firstly guys, this is the concept that I have created myself and you will not find this sign convention in any book or on the internet. This is a concept that I have created for my own convenience in order to solve questions. And I guarantee you, once you know how to apply this, you will be able to solve every SFD and BMD question. So first of all, we will look at case 1. Now suppose that a beam is given to us and we have to find the SFD and BMD while going from left to right. That is, we will go from the left end of the rod or the beam to the right side. For that we have the sign convention like this. Now suppose that a force is being applied on the left hand side from the top, that is, it is acting downwards, then it has to be taken negative. And similarly, while still going from left to right, a force is being applied upwards, that is from the bottom of the beam, that is, its direction is like this, then it has to be considered to be positive. Now guys, this sign convention when you go from left to right is valid for both, that is for SFD and BMD both. That is, you will use it for SFD and BMD similarly. That is, when you are going from left to right, this sign convention will be used for both SFD and BMD. There is no difference between the two when you are going from left to right. Now guys, we will see case 2. Now suppose that a beam is given to you and you have to find the forces from right to left. That is, you are going from the right hand side to the left hand side of the beam. Now first of all, we will do for SFD. Now suppose we are going from right to left. Now the forces that are acting downwards or that are denoted by the arrow that is pointing downwards, those forces are to be taken positive. Now similarly, the forces that are acting upwards, that is from the bottom of the beam, they are acting upwards, they are taken to be negative. Now this sign convention is only to be followed for SFD when you are going from right to left. Now similarly, when we are going from right to left, we will look for BMD, that how we have to apply the sign convention over here. Now suppose the forces that are acting downwards on the right hand side, that is the arrow is pointing downwards, they are to be taken negative. And the forces that are acting upwards, that is the arrow is pointing upwards, they are taken to be positive. Now this sign convention is only to be applied when you are solving for BMD and moreover you are going from right to left. Now guys, you will notice that when you are going from left to right and right to left, the sign convention for BMD remains the same. That is, in the case of a BMD, you will apply the same sign convention irrespective whether you are going from right to left or from left to right. That is, I have written over here. Now, but for SFD, both the sign conventions are different. That is, from left to right, the sign convention is this, and from right to left, this is the sign convention. Now guys, please keep these sign conventions in mind because we will use them in solving every question. And if you are not familiar with these, you will not be able to solve any question on BMD or SFD. And guys, I advise you that you do not follow the sign conventions which are given in the books or which are provided on the internet, as they are very confusing and they would create a lot of problem while solving questions. Please follow this sign convention and I guarantee you that you will be able to solve every SFD and BMD question. So first of all, we are going to look at question number 1. Now guys, in question number 1, we have to find the SFD and BMD for the given cantilever beam. And guys, this red part that is shown in the figure is the UDL, that is uniform distributed load. And this UDL is distributed along the whole beam. And the force on it is given in the terms of kilonewton per meter. That means in 1 meter of this UDL, the force being applied is 20 kilonewton. So for the whole UDL, the force being applied will be 20 into 3, as the length of the rod is 3. So now guys, we will see that how we have to solve questions when UDL is given along with a cantilever. And also keep one thing in mind, that whenever a cantilever is given, that is, it is fixed on the right side in this question. So we will start finding our forces from the left hand side. And if the cantilever had been on the right hand side, that is if the beam had been fixed on this side, then we would have started from the right side. So now we will proceed with the question, and first of all we will find SFD. Now guys, in order to find SFD, first of all we will consider an element or a part of this rod to be at a distance x from A. Let us say this is distance x from the A part to this point. So first of all, we are going to look between A and B portions of the beam. That is, first of all, we will find for portions between A and B. So now we will write the equation for the shear forces only for this part of the beam. That is, we will write S of x is equal to 20 kilonewton minus 20 into x. Now guys, you must remember that previously we discussed the sign convention. So as we are moving from left to right and we are finding for SFD, so the forces that are acting downwards or the arrow is pointing downwards, so we will take them as negative. So over here we have two forces which are acting downwards between A and B, excluding B. That is, we will not take the 40 kilonewton force over here. That is, this force 20 kilonewton is acting downwards, and guys, this force also is acting downwards. Now you must be thinking that this force is acting between B and C, but this is not the case, as it is a UDL force. That is, it is acting over the whole uniformly distributed part, that is the red part. That is, for now we are considering only A and B part, and in A and B part also we are considering only this part, that is till x. That is why we have multiplied this force by x, because we are considering this distance first, that is only this part of the UDL. And as we know x is in meters, so when we multiply x by 20 kilonewton per meter, it becomes the unit of kilonewton. So now we will further solve our question. That is, first of all we will consider point A. That is, we will write shear force at point A. So in the value of x we will put 0, because we know that A is the starting point of the rod, that is, we can say it is the origin. So we will replace the value of x as 0, and in that case we will get the answer as minus 20 kilonewton. This is our shear force for A. Now guys, similarly we will find for B, that is in this equation only we will find the shear force for B. That is, we will replace the value of x as 1, because we know that from the origin point or this point the distance of B is 1 meter. So therefore we will replace x by 1, and on doing that we will get the value as minus 40 kilonewton. Now guys, we have found out the shear forces at point A and point B. So now we will similarly find the shear forces between B and C. For that we will consider the portion over here, that is the 2 meter part. Now I know guys that this part is a little tricky and you must be having difficulty in understanding this part. But do not worry, we will be doing more questions which will help you understand this. So now we will proceed similarly in order to find the SFD between B and C. Now guys, previously we found out the shear forces at points A and B, so now we are going to consider this part. So over here also we are going to consider another element at a distance x from point A. Now we will ignore this part, that is, now we will consider a new element x over here, and we will not be considering the x that we assumed previously, that is, we can ignore this now. So now we are going to write the force equations as we wrote for A and B. That is, we will again write this as F SFXX is equal to minus 20 minus 40 minus 20 into x. And guys, you should not be having any problem with these negative signs, as we are simply now applying the sign convention as we discussed earlier. That is, when we are moving from left to right and the forces are acting downwards, then we will write them as negative, and the forces which are acting from below, that are upwards, we will take them as positive. But as in this question we do not have any upward forces, we only have downward forces, so all the forces are coming out to be negative for SFD when we are moving from left to right. Now this part, that is the UDL part. Now guys, we are considering only this part of the UDL till the point x that we have assumed. That is why we have multiplied this by x in order to convert it into the form of kilonewton. That is, we have converted into the form of 20x kilonewton. Now guys, we will simply put the values of x, that is, first of all we will find shear force at B, and we will put the value of x as 1, because the distance of point B from A is 1. So on putting the value of x as 1, we will get the value of B to be minus 80 kilonewton. Now guys, similarly we are going to find for C, that is, we will write shear force at C, and now we will replace the value of x by 3, as we know that the distance of point C from point A is 3 meters. That is why we will replace it by 3. Now on solving this you will get 120 kilonewton. Now guys, I will again explain this part in order for you to understand it clearly. That is, we first wrote minus 20, minus 14, minus 20x. This part you must have understood, as we have simply applied the sign convention. And we have multiplied this by x because we are only considering this part of the UDL, which is at a distance x. That is, this is the distance x. And guys, similarly, when we are finding for B, we have to consider its position from the point where we are starting to find the forces. That is, we had started from A point. So the distance of B from A is 1 meter. That is why we replaced x by 1. And similarly, we have replaced the value of x for C as 3 meters, because the distance of C from A point is 3. So on doing that, we have got our necessary shear forces. Now guys, using these values of shear forces at A, B and C, we are going to draw the SFD, that is the shear force diagram. Now guys, previously we found out the shear forces at A, B and C. So now we are going to use them and draw our SFD. That is, first of all, on the axis we are going to put the points A, B and C. Now firstly we found out the value of shear force at A to be minus 20 kilonewton. So we are taking it downwards as it is negative, and we will write here minus 20 kilonewton over here. And now similarly SFB came out to be minus 40 kilonewton. So we will move this linearly to the minus 40 kilonewton point. And guys, when we found out the shear forces between B and C, the value of SFB, that is the shear force at B, came out to be minus 80. So now we will move this straight to the point of minus 80 kilonewton. And similarly our SFC, that is the shear force at C, came out to be minus 120 kilonewton. So we will move this linearly towards that point, that is towards the minus 120 kilonewton point. So guys, this is the shear force diagram, that is our SFD, and this has come out to be negative, that is, it is below the axis. Now guys, in the shortcut procedure we had discussed that whenever we have a UDL, a graph for SFD would come out to be linear. So this has come to be a linear graph, that is, the lines are straight. So now we have drawn our SFD. Now we are going to draw our BMD, but before doing that we will have to find the bending moments at points A, B and C as we found out for SFD. So guys, now we are going to find out BMD between the points A and B. So similarly as we considered in SFD, we are going to consider an element at a distance x from the point A. So now we are going to write the bending moment equation between points A and B. That is, we will name it as BMX x is equal to minus 20x into x by 2. Now guys, I'll explain this equation, that how we got this. So first of all, I'll explain you the difference between an SFD equation and a BMD equation. In SFD equation we only consider the forces, but in BMD equation we also consider the forces multiplied with the length that we are considering. That is, in this part we are considering the length x. So we have multiplied minus 20 into x, that is, we have got the bending moment, and the formula also for bending moment is force into length. And similarly, as we discussed earlier, that this is the UDL force which is applicable for all the red part, but we are only considering this part. So first of all we wrote 20 into x, that is, we converted into kilonewton form, and then we took half of this x and multiplied by it. That is, keep this in mind, that whenever you are taking UDL, first you multiply it by the total distance that we are considering, and then you multiply by half that distance. That is, suppose we considered x, so we multiplied first it by x in order to convert it into the form of 20 kilonewton. Now similarly, in order to convert it into a BMD form, we will multiply it by half the length that we have assumed, that is x by 2. So now guys, we are going to find bending moment at point A, that is, we will name it as BMA. So here we are going to put the value of x as 0, because A is itself the starting point, so its distance will be 0. So on replacing x by 0 you will get 0. So the bending moment at A is 0. Now we will similarly find the bending moment at B. Now guys, we can see that the distance of point B from the starting point, from where we started to find our forces, is 1 meter. So we will replace x by 1, and from there you will get minus 30 kilonewton meter. And please see that the units are also different, as now we are multiplying the length also along with the forces. Now guys, similarly we are going to find the BMD between points B and C. That is, now also we are going to consider a point x over here, and we will ignore this part as we considered it earlier. Now we are going to write the normal BMD equation for it also. That is, we will write it as BMX x is equal to minus 20x minus 40 into x minus 1 minus 20 into x by 2. And guys, this is a very tricky equation and I'll explain it step by step. So now first of all we have written minus 20 into x as we wrote earlier, because we are considering the downward force and the sign convention for that is negative. And as it is a BMD, we have multiplied the length x that we have considered now. And similarly for 40 we have taken the negative sign as it is also a downward force. And now we have multiplied it by x minus 1. Now this is an important point, because now it is at point B, which is at a distance of 1 meter from here. But we are finding the bending moment for this part, so we will only take this length. And as we have considered that from this point to the point A, the distance is x and this length is 1 meter, so this length will come out to be x minus 1. That is why we have multiplied by x minus 1. Now in this, guys, that is the UDL part, we first simply converted into the form of 20 kN by multiplying x. Now the x by 2 part, as I explained earlier, that we have to multiply the UDL forces by half the distance that we have assumed. That is, again we have assumed the distance to be x from point A to this point. So half of that will be x by 2. So we multiplied this by x by 2. Now guys, do not worry if you did not understand this here. We are going to do more questions in which it will become very clear to you. So now similarly we are going to find the bending moment at point B. That is, we will name it as BMB. And we will replace the value of x by 1. On doing that, you will get minus 30 kilonewton meter. And we replace x by 1 because the distance of B from the starting point is 1 meter. And similarly, when we will find the bending moment for point C, we will put the value of x as 3, because the distance of C from the origin is 3 meters. That is why on doing that, you will get the value of bending moment at C to be minus 230 kilonewton meter. Now guys, we are going to use these values of bending moment, that is at A, B and C, to make the BMD, that is the bending moment diagram. Now guys, these are the values of bending moments that we found out previously. Now we are going to use these to find out the bending moment diagram, that is our BMD. So first of all we are going to draw the axis and we will name it as A, B and C. And guys, the BMD, that is the bending moment at A is 0, so we will start from here, that is the origin. And we found out the bending moment to be minus 30 kilonewton meter at point B, so we will draw this till there, that is we will draw a curved graph. That is, this is our minus 30 kilonewton meter part. And similarly at this point, that is between B and C, the bending moment again came out to be minus 30 kilonewton meter. So this part will remain as it is. And the bending moment at C came out to be minus 230 kilonewton meter. So we will extend it till that part. That is minus 230 kilonewton meter. Now guys, you must be wondering that why we made a curved graph. Now please remember that in the shortcut procedure method we discussed before, we stated that when we have a UDL load, that is a uniformly distributed load, then our BMD graph would come out to be parabolic. So this is our parabolic shape. And our SFD came out to be linear. And guys, please do not draw these lines to be straight, as these are parabolic lines and not linear lines. So now guys, this is our final BMD graph, and we found out the SFD graph initially. So these two graphs are the final answer that you'll have to show in the examination along with the working. So now we are going to do question number 2 in order to get a better hold on our concepts. Now guys, in question number 2, we have to draw the SFD and the BMD of the following beam. But before doing that, we have to find the value of RA and RB, which are the unknown forces. So we will find them by considering a point A and taking moments across it and equating it to 0. That is, we will take moments across A and equate them to 0. That is, we will take the clockwise rotation to be positive and anti-clockwise rotation to be negative. That is, first of all we will write for this. That is, we will write 30 into 3. We have written this to be positive as it is clockwise. That is, as we are considering this point A and force of 30 kN per meter is applied over here, then this rod will move in clockwise direction. That is why this is taken to be positive. And we have multiplied by 3 because this is given in the units of kilonewton per meter. But we need the force being applied by this whole ULD part. That is the uniformly distributed load. That is why we have multiplied by 3. Now similarly guys, we are going to take the moment for 20 kilonewton force. That is 20 into the sum of this length. That is 8 minus RB. RB into 6 is equal to 0. We have taken RB into 6 to be negative because this will move the rod in anti-clockwise direction. Now guys, from here we will find out the value of RB. That is, on solving you will get RB to be equal to 49.167 kilonewton. And now guys, that we have found out the value of RB, now we will find out the value of RA. For that we are going to equate the forces which are acting upwards and which are acting downwards. That is, first we will write the forces which are acting downwards. That is 30 into 3 plus 20. These are the forces that are acting downwards. We will equate it to the forces which are acting upwards so that the equilibrium is maintained in the beam. So now we are going to write RA plus RB. And we will put this value of RB over here. And from here we will get the value of RA to be 60.833 kilonewton. Now guys, that we have found out the values of RA and RB, now we are going to find the shear forces at points A, D, B and C. And then subsequently we are going to find the bending moments at these points. And then we will draw their diagrams. So first of all we will find the SFD. So now guys, we are going to find the shear forces at points A and D. So first of all we will consider only this part. That is the part between A and D. So we will first assume an element to be at a distance x from point A. So now we are going to write the SFD equations. That is, we will name it as SFXX, which will come out to be RA minus 30 into x. Now guys, we have written RA to be positive because it is a force which is acting upwards. That is, the arrow is pointing upwards. That is why we have written it to be positive. Now similarly, we have written minus 30 into x because this is the force which is acting downwards. And we have multiplied by x because this is the portion of UDL that we are considering. So now we are going to find the shear force, that is SFA, at point A. So now we will replace x by 0 because we have considered A to be the origin. That is, we have started from that point. So from that we will get the shear force at A to be equal to RA, which is equal to 60.83 kilonewton, as we found out previously. Now similarly, we are going to find out the value of shear force at point D. And here we will write the value of x as 3. That is, we will write 60.83 minus 30 into 3. On solving this, you will get minus 29.17 kilonewton. Now guys, this is our shearing force at point D. Now similarly, we are going to consider the part between D and B in order to find the shear forces at point D and point B. That is, we will neglect this point and we will now draw a new point over here at a distance x. So now guys, considering the points between D and B. So first of all we are going to write the shear force equation, which will come out to be RA minus 30 into 3. Now guys, you will see that we have force RA which is acting upwards, so it is taken to be positive, and similarly we have taken the UDL force which is acting downwards to be negative, and we have multiplied by 3 because now we are considering this whole part of UDL. So now we will find out the value of shear force at point D. That is, we will write it as SFD. Now here you can see that this equation is independent of x. So the value of shear force at point D and shear force at point B will come out to be same. That is, on solving this you will get minus 29.17, and similarly shear force at B you will also get minus 29.17 kilonewton. Now guys, subsequently we are going to look between the portion B and C. That is, now we will consider a new element which will be at a distance x from the point A. So we will neglect this x and the previous x also. So this is the new element which is at a distance x. So now we are going to write the SFD equation for the portion B and C. That is between B and C. Our SFD equation will come out to be RA minus 30 into 3 plus 49.16. Now guys, this is the RA part which is taken to be positive because it is the force which is acting upwards, and similarly we are taking this to be negative because it is acting downwards. That is our normal sign convention. And over here RB is acting upwards, so we have taken it to be positive. This is the value of RB. And guys, for finding the SFD we don't have any use for this because we are going from left to right, so we won't be considering this force. But if we had been going from right to left, then this force would have been neglected. So now from here you can see that this value is also independent of x. So from here the value of SFB, that is the shear force at B, will come out to be 19.99, which is approximately 20 kilonewton. And similarly the shear force at C will also come out to be approximately equal to 20 kilonewton. Now guys, that we have found out the shear forces at A, D, B and C, now we are going to use them and draw the SFD, that is the shear force diagram. And guys, writing these equations, that is the SFD equations, is the main step in solving these questions. So please keep them in mind and do not mix up with the sign convention. So now we are going to draw the SFD. So now guys, as we have found out the values of shear forces at A, D, B and C, so now we are going to draw the SFD. And guys, I have also written both the methods that we used for this part. That is, the first method is from L to R, that is from left to right, and the second method is from right to left. This is the shortcut part, but which is only valid for the B and C part. Now guys, we are going to draw the SFD. That is, first of all, we are going to take the axis and we are going to put the points A, D, B and C. So now first of all we know that point A has a force of 60.83 kilonewton, and similarly the value of D is minus 29.17 kilonewton, so we will take it till that point, that is minus 29.17 kilonewton. And guys, we know that SFD, that is the shear force at point D, is equal to the shear force at point B. So it will be a constant line joining these 2 points. That is, this is also a point of minus 29.70. And guys, secondly, that is in part B and C, we found out that the value of shearing force is 20 kilonewton. That is, we will take it to the 20 kilonewton point. That is over here. And similarly, the value of SFC, that is the shear force at point C, is also 20 kilonewton. So we will draw a straight line joining point C and point B. Now guys, this is a point at which our shear force is 0. So in some of the questions we are also told to find this distance, that is this distance x, from the origin to the point at which the shear force becomes 0. So now as we can see, this point lies between A and D. So we will go to the point where we have considered A and D part. So here we are going to take this equation and equate it to 0. On doing that, you will get the value of x as 2.028 meter. That is, we have got this by simply equating this equation to 0. So this is the value of x. And guys, you will notice that in the part of the ULD, that is the part between A and D, our graph has come out to be linear, as we discussed earlier. And the part in which there is no load, that is between the part D and B and C, there is no load. So our graph has come out to be constant. Now similarly, we are going to keep these concepts in mind and we are going to find the bending moments at point A, D, B and C. And using them, we are going to draw the BMD. Now guys, we are going to find the bending moments in this beam. So first of all, we are going to consider the part between points A and point D. That is, we will find the bending moment between A and D. So we will write the BMX, that is the bending moment equation, which will come out to be RA into x minus 30 into x by 2. Now guys, you must remember that in bending moments we have to multiply the force by the length that we have considered. That is, in this part we will consider a point which will be at a distance of x from the point A. Now here RA we have multiplied by x because this is the length that we are considering, and similarly we first multiplied the portion that we are considering for UDL and then we multiplied by the half of the assumed length as we discussed in the previous question. Please keep this concept in mind as this is very important. Now we are going to find the value for BMA, that is the bending moment at point A. Now as we have considered A to be the origin, so the value of x at point A will be 0. So on putting the value of x as 0 in this equation, you will get bending moment at A to be 0. Now similarly, in order to find the bending moment at point D, we are going to put the value of x as 3 meters, as D is at a distance of 3 meters from point A. On putting 3 instead of x in this equation, you will get the value of bending moment at point D as 47.5 kilonewton. Now guys, similarly we are going to consider this part, that is the part between D and B. So first of all we are going to consider an element which will be at a distance x from point A, that is, this is the distance x, and now we will neglect this part, that is, we will not be considering this part. So now we are going to write the bending moment equation which will come out to be RA into x minus 30 into 3 into x minus 1.5. Now guys, we have simply used the sign convention, that is, first of all we wrote RA into x, which will be positive because we are considering for B and D and we are moving from left to right, and similarly we have taken minus 30 into 3 because this is the part of UDL that we are considering, that is, now we are considering the whole part. And guys, we are going to discuss a new concept over here, that is, whenever we are doing for a part in which the ULD is not involved, that is, we are looking at the part D and B, and over here the UDL is not involved, that is, UDL is not present here. So in order to find the length that we have to multiply to the force in order to find the BMD will be taken like this, that is, first of all we will write x, that is the distance of the point that we have considered from point A, and secondly we will subtract it from half the length of the ULD, that is 3 by 2, which will come out to be 1.5. Now suppose if this had been 4 over here, then we would have written x minus 2, that is x minus 4 by 2. So guys, this is a very tricky part. I'll explain it again. See that if ULD is not present in the part that we are considering, that is, we are taking the part D and B and ULD is not present over there. But in order to find a BMD, that is the bending moment, we have to multiply length into force. So in order to find the length which we have to multiply to the force by the ULD, we will first write x, then we will subtract it by half of that ULD's length. So guys, now we are going to find the value of BMD, that is the bending moment at point D. So we can see that D is at a distance of 3 meters from A, so we will replace x by 3. On doing that, you will get the value of BMD as 47.49 or 47.5 kilonewton. Now guys, we are going to find bending moment at point B. That is, we can see that point B is at a distance of 6 meters from point A. So in this equation, we will replace x by 6. On doing that, you will get the value of BMB as minus 40.02 kilonewton. Now guys, similarly, in part B and C, we are going to use the concept that we use for SFD. That is, for this particular part, we will move from right to left. And for that, we will get the equation as BMX is equal to minus 20x, as we are using the particular sign convention to find BMD. Now similarly, we will replace x by 0 when we have to find BMC, that is the bending moment at point C, because now we are considering this to be the starting point. So here we will get the bending moment to be 0. And similarly, to find the bending moment at point B, when we are between B and C, we will replace it by 2 meter, because now we are moving from right to left. So on replacing x by 2 in this equation, you will get BMB as minus 40 kilonewton. And over here also, minus 40.02 Newton can be written as minus 40 kilonewton, as it is approximately equal. So guys, we have found out all the bending moments at these points, that is A, D, B and C. So now we are going to use these and draw the BMD. Now guys, as we have found out all the bending moments at these points, that is A, D, B and C. So now using them we are going to draw the BMD, that is the bending moment diagram. So first of all we are going to draw the axis and mark the points A, D, B and C. Now we can see that bending moment at A has come out to be 0 and bending moment at D is 47.5. So this part will be parabolic, that is still 47.5 kilonewton. This is because between the part A and D we have a UDL, that is uniformly distributed load. And similarly we can see that in the second part between D and B, bending moment at D has again come out to be 47.5 kilonewton. So this part will remain over here. And similarly we found out BMB to be minus 40 kilonewton. So now we are going to take it linearly to the point of minus 40 kilonewton. We have drawn this to be linear as no load is applied at this point, that is between the parts D and B. And again we found out the value of BMB, that is bending moment at point B, to be minus 40 kilonewton between the parts B and C, and C came out to be 0. So we will simply join this to the C point, that is at point 0, and this is again linear because no load is applied at the point B and C. So guys, this is our final BMD, that is bending moment diagram. Now guys, I hope that you have now understood how to solve SFD and BMD questions using the concepts that I have explained. And if you want me to do more questions on SFD and BMD, please write in the comment section, or you can DM me on Instagram at Blazengg Academy. I have provided the link in the description below. And guys, I hope that you understood this. And SFD and BMD is a very important part of basic mechanical engineering, as 1 or 2 questions are always asked in the exam. And guys, this is no doubt a very difficult and a tricky subject, so please take your time while doing it. Now guys, after watching this video, please do not forget to subscribe, like and comment.